Okay, guys, we're going to talk about half-life today, which I know is something that you talked a little bit about in biology. But just so that we know kind of the definition, is that half-life is defined as the time required for 1/2 of the reactant to react. So it's talking about half of what we started with to be gone. Because the concentration of A at T1/2 is 1/2 of the original, we can kind of come up with this equation here. Is that so at any specific time, we are half the original concentration, or not at any specific time, sorry, at the half-life time. We are half the concentration originally. So when we look at the graph, if we're doing pressure, remember pressure is a way we can measure the concentration of gases. And we say, okay, we started with 150 atmosphere or torr as our pressure. When we hit 75, we know that half of it is gone. Then we can do another half-life. So when we know we get to 37.5, another half is gone. So a second half. We could keep going, and then eventually our line kind of flattens out as the reaction reaches equilibrium, and it becomes super, super small values. So we are going to look specifically at first order and second order half-life. We are going to only calculate it for a first order process though. So the cool thing about first order process is that, remember we said when you graph the natural log of the concentration versus time, you end up with a straight line. So when we rearrange that equation a little bit, we actually end up canceling out our initial concentration. And the half-life of a first order reaction is completely independent of the initial concentration. So it doesn't matter if we start with 1 mole of something, or if we start with 5 moles of something, or 100 moles of something. When we are looking for the half-life of a first order process, this is going to be the equation that we use. So if we know the time for the half-life, this is another way that we can find our rate constant, K. If we know our rate constant for the reaction, then we can rearrange and we can solve for the half-life. Okay, so it does not depend on the initial concentration. It is always this equation, no matter what the scenario is, if it's first order. Okay, so let's look at this. Reaction is first order in A. If the rate constant of the reaction is 6 times 10 to the negative third seconds to the negative 1, what is the half-life? So we're looking for half-life here. So we're going to do 0.693 divided by K, which is 6.00 times 10 negative third seconds to the negative 1. So I'm going to do that in my calculator, 0.693 divided by 6.00 e to the negative third. And we will end up with 115.5, and seconds to the negative 1 is going to move to the top. So we're dividing by it. And the half-life of that process is 115.5 seconds. So it's really simple to calculate the half-life of a first order process because it is not dependent on the concentrations. So let's look at one more here. This one is asking for what is the rate constant. So take a second, rearrange the equation and solve, and then check your answer. Okay, so when I rearrange, I'm dividing by the half-life. So I'm going to take my 0.693 divided by 0.100 seconds, and that gives me a rate constant of 6.93, 1 over seconds, or seconds to the negative 1. This equation up here is given to you on your gold sheet for the AP test. So you need to know when to use it, but you don't need to have it memorized. A second order half-life is a little bit more of a process, only because the concentration does impact the half-life. So it's 1 over the rate constant times the initial concentration is going to equal the half-life once we kind of rearrange our equations here. I will not ask you to do calculations with the second order half-life, and it is not going to be on the AP test to calculate that. So there you go.